Yeah, because they don't want people to just get married, get a green card, and then immediately get divorced. Okay, so I'm just doing the process of renewal after.
Where if you want. Yeah, keep looking.
I had a feeling. Conjectures.
Yeah, it's about
Yeah, there are quotas. It also depends what country you're coming from. You have to work yeah, it's not exactly. I think it's about how many people come from that country. So, like, it's not about what's on countries. Like India, more of a problem because so many people are trying to.
No, not that one.
It should be there. Plausible to try, or is
Okay, good afternoon. Next speaker is Adam Sheffer. He will talk about connections between discrete geometry and additive combinatorics.
Thank you. Do you hear me okay with the microphone? Okay. Hi. So, yes, I'm going to talk about the connection between discrete geometry and additive combinatorics, and I'm sure most people here know about a lot of such connections. Two fields have a lot of interesting connections, and I'll talk about another one that I'd like to call geometric energies. So there's a paper behind this, a recent paper, but in some sense, my goal is not to convince you that this is an amazing paper or anything. That's not what I'm going to try to do here. My goal is to try to convince you that there's some sort of unexplored territory here that has a lot of interesting things going on in it. And maybe I'll manage to convince one or two of the people here that it's worth studying more seriously. Okay, so the work that I will mention, it's a joint work with Cosmin Pohoata, somewhere here in the back. He's a graduate student in Caltech of NetSCATS. Okay, and I'd like to start by upsetting a lot of people in the audience by repeating very, very basic things that you all know. So I'll start by defining stuff that everyone knows. If we have a finite set of numbers, let's say real numbers, we all know what a subset is. I should say Misha gave a great background for the talk that I'm going to give now, thank you. Subset, the set of all sums of pairs of elements from our set. And most sets will have a very large sum set. We don't expect many sums to be represented more than once, so it's about a squared. There are some sets that have a very small sum set because, well, for example, arithmetic progressions and related sets, we sometimes say that they have some sort of an additive structure that gives them a very small subset. And people study this additive structure, whatever it means. So, for example, for R, we have this variant of Primon's theorem. It tells us if a set has a small subset, then it is contained in a generalized arithmetic progression. I'm, of course, ignoring a lot of details here. But the point is, we know that if there's a small subset, there's some sort of additive structure. Okay, another very basic concept that also Misha talked about is additive energy. So if we have a finite set of numbers, the additive energy, the number of quadruples A, B, C, D in our set, such that A plus B is C plus D. We have two representations of the same sum. And it's very easy to show the energy is at least A squared because there are A squared degenerate quadruples where A and C are the same, and B and D are the same. It's also very easy to show that it's at most A cubed because after fixing A, B, and C, there's at most one valid value for D. Okay, so some set goes between A squared and A, kind of A and A squared. Energy goes between A squared and A cubed. And there's some kind of a correlation between them, not exactly. So for one direction, if there's a small subset, we know that this means that the energy is very large. You can easily show using Cauchy-Schwarz, small subset implies large energy. The other direction is not exactly true. You can have a very large energy in a very large subset or small subset. It doesn't tell you exactly. And that's why one way to handle this is a variant of the Balog-Samredy-Gowers theorem that tells us if there's, again, this is not a rigorous way to write anything, but one way to say Balog-Samredy-Gowers, what it does is it says if there's a large additive energy, that means that there's a large subset that has a good additive structure. There might be a lot of noise around it, but there is some structure underneath after you remove. Okay, so after briefly upsetting people with basic additive combinatorics definition, let's upset some other people with basic discrete geometry definitions. So I want to remind you what distinct distances are. So in this problem we have a set of points, let's say in the plane, and we look, just like we looked at the set of all sums that we have for every two elements, we now look at all the distances. For every 2 points, what's the distance between them? We look at the set of these distances. So for example, this is supposed to be a set of 5 points, kind of a house-shaped set. And you can count, there are only 4 distances here. There's supposed to be a square, so all of these are the same distance. The diagonal repeats twice, some more repetition, so we only have 4 distinct distances in the distance set. And here's a different set of 5 points in the plane. It's supposed to be a regular pentagon. In a regular pentagon, we only have 2 distances. All the sides are the same distance, so that's 1. All the diagonals are the same distance, so that's a second distance. And Erdős asked, many years ago, what is the minimum number of distinct distances that can be spanned by n points in the plane? So we're going over every set of n points, and we're asking how few distances can we have in the distance set. Maybe the easiest example to see what's happening in it is taking n points evenly spaced on the line. If we have n points evenly spaced on the line, it's very easy to see that the number of distances here is exactly n minus 1. Because take any distance, I don't know, this distance, it also happens with the leftmost point at some other point. So you just need to see what distances are spanned with the leftmost point, n minus 1. Okay. Another easy example is taking the vertices of a regular n-gon. It's very easy to see there's a lot of symmetry here. It's enough to look at one point again, and you have about half an n distances. So it's kind of easy to get to sets with about n distances that define only n distances. And originally, in his original paper, Erdős showed that you can do asymptotically better. There are sets of points with a sublinear number of distinct distances. He took a section of the integer lattice, square root of n by square root of n section of the integer lattice, and showed that it has n over square root of log n distinct distances, and he conjectured that this is tight. Okay, so that was the simpler part, I guess. How do you show that this is tight? You need to show that every set of endpoints in the plane determines at least this number of distances. This turned out to be a lot more complicated. And let's sort of put this list that everyone used. A lot of people worked on this. There was constant progress showing every set of endpoints in the plane has at least this number of distinct distances. You can see a lot of interesting people worked on this problem. And around 2010, Guth and Katz almost completely settled this problem. They show that every set of endpoints in the plane determines at least n over log n distinct distances. So this was not a tight bound. The conjecture is that every set of points should have at least n over square root of log n. There's still a tiny gap of a square root of a log, but it's a very small gap. It's no longer polynomial in, and it's kind of considered mostly solved. And Guth and Katz introduced a lot of new ideas to solve this, all of these polynomial techniques. And I guess when this happened, people seemed rather optimistic that now we can use all of these new techniques, new polynomial techniques, to solve the other related big open problems. But somehow it seems that in the time that has passed, most of the main open problems related to this are still just as open as before. New techniques were not adapted to them yet, and I thought I'll briefly mention just a couple of those. So what seemed to me like the main related open problems now, so there's the problem in higher dimensions. What happens if you have distinct distances, you have endpoints in a d-dimensional space? What's the minimum number of distances you can have? And you can easily show that there's a set of endpoints in d-dimensional space with n to the 2 over d distinct distances. Again, a section of an integer lattice. And this is conjectured to be tight, but now there's still a polynomial gap. Even in 3 dimensions, we still don't know. There's been a lot of attempts to generalize what Guth and Katz did to R3. So far, there's progress, but we're still not there. Now, I'm a bit, maybe you think you wouldn't agree with me, but I'm a bit optimistic about this. I think we're slowly learning how to adapt all of the techniques from the plane to higher dimensions, and probably in a few years we'll already have this in any dimension. Oh, maybe I'll just mention the best bound in higher dimensions so far is by an older paper of Shoimoshi and Wu, combined with what Guth and Katz did. So there's a second problem that I think is much more challenging. Again, you might not agree, but this is a problem that's not clear to me if we are close to having the right tools to handle this at all. Maybe we're 100 years away from it, I don't know. And it's to characterize sets of points that have small number of distances, maybe n over square root of log n distances. How do they look like? And this is an old problem. It exists for many decades. And we just don't know anything. You can find a million conjectures, hardly any piece of information. And just to show you how embarrassing this situation is, so I'll mention briefly what's conjectured. So Erdős conjectured many decades ago that a configuration with a small number of distances should have lattice structure. What's lattice structure? Unclear. He says it's not the next sentence in the paper is that it's not really well defined. There are all sorts of people who think different things about what it should mean. This is very hard. We don't know how to do this. So Erdős conjectured, let's show that if there's a set with few distances, maybe we can cover it by a relatively small number of lines. It's not a lattice, but it's kind of a step towards a lattice, right? Still, extremely difficult. How do you do such a thing? So Erdős conjectured, maybe we can show that if a set has a small number of distances, there will be a line that contains square root of endpoints. And this is every example that we know with few distances. There are many lines with square root of endpoints. Still, no one has any idea how to do such a thing. And the situation is so bad that decades ago, Erdős conjectured, can someone show that there's a line with n to the epsilon points on it, for any epsilon, as small as you like, if there are few distances? No one knows how to do this. I always think you want to laugh at people who work on these problems. This is a good way to laugh. Like, we don't know how to do this much weaker thing. What is known? So there's an old proof of semi-ready from the 70s. You can adapt to get a line with square root of log n points on it. And if you use some more recent tools, it immediately becomes log n. It's not something complicated. It's just we have newer tools, you now get log n from this. So this seems like a very difficult problem. There are a lot of other conjectures related to this structure, and we just don't really know much about the structure of sets with few distances. Okay, last piece of basic information I wanted to say before we get to what I want to talk about. I'm not going to tell you how to prove anything about these distinct distances problems. I just want to mention that in a lot of these papers there's the same tool. And not just this, also in a lot of related works, you use this technique. So let's say we have endpoints. Let's say the number of distances is x. We want to study the number of quadruples of points such that this means Euclidean distance. A and B has the same Euclidean distance as C and D. And this was used by Guth and Katz. It was used before Guth and Katz, after Guth and Katz. It's a very common technique. How do you use this? So very briefly, simple use of Cauchy-Schwarz shows you that the number of quadruples is at least n to the 4 over the number of distances. Now if you have an upper bound for the number of quadruples, Guth and Katz showed this upper bound, you combine the upper and lower bounds, and you get a lower bound for the number of distances. So Guth and Katz showed for every set of endpoints in the plane, there's at most n cubed log n quadruples of this sort. Pairs of two different representations of the same distance. And that's how they got this. Now, of course, I'm completely ignoring all the brilliant ideas from their paper. This was not a new idea or anything. But you see where I'm going with this, right? It's not hard to see what I'm trying to say here. This looks the same, right? So we have, and this is not new. I'm not trying to say anything new yet. So in additive combinatorics, one of the main tools is the additive energy. It's the number of quadruples that satisfy this condition, two representations of the same sum. In the discrete geometry, we have all sorts of problems where we look at the number of quadruples where, for example, they satisfy the same distance. So maybe you can think of it as distance energy. Let's call it distance energy, because instead of addition, we're looking at Euclidean distance. Okay, so far this is maybe just a cute resemblance. I'm not saying anything useful, right? And when you start looking at it, you see all sorts of cute analogs like this. For example, so we had Feynman's theorem. Feynman's theorem tells us in one phrasing is you have few sums, their structure. You're in a generalized arithmetic progression. So you can think of the hard open problem I just mentioned. It's kind of a distance variant of Feynman's theorem, right? You're asking the small distance set means structure. It's kind of a distance variant of the same thing. You can call it a distance prime. I don't know. Doesn't say much, right? It's not helpful in any way. Similarly, Baloch-Samardie-Gowers. The way the variant I presented was large additive energy means large subset with a small subset, or large subset with structure, right? And you can say what would be a distance variant of Baloch-Samardie-Gowers. So you can say maybe it would be large distance energy means large subset with a lot of structure, right? This would be amazing. This would be if you get a much weaker than this. The large distance energy means some sort of structure. It would still be by far probably the largest structural result we have for such a problem. Kind of a distance Baloch-Samardie-Gowers. Okay, so far I'm not really saying much, right? I'm just saying, look, it looks similar. But why? Why is it useful? So I'm going to try to convince you that it's useful. But before that, I just wanted to mention that this is only one type of geometric energy. You can think of a lot of types of geometric energies. For example, a few years ago, we had a work studying what we call bisector energy. What is bisector energy? We're looking at quadruples of points just like before. And we'd like to say, now we're asking the perpendicular bisector of A and B, which is a line, to be the same line as the perpendicular bisector of C and D. So it's another type of a geometric energy, right? You want to have the same perpendicular bisector now. And we use this to study sets with few distances. For example, by getting bounds for bisector energy, so I should say this was a work with Ben Lund and Frank Lejeune, also in the audience here. I can look at them there or here. So what we used, one of our uses for bisector energy was if you have a set of endpoints in the plane with a few distances, either there's a line or a circle with a lot of points, which is kind of the holy grail, right? It's showed that if there's few distances, there's a line with many points on it. But we have a second option, or there are really a lot of lines with square root of log endpoints, which seems like also some sort of structure, right? We know that then the set has a really large number of lines with a lot of points on them. Sounds like you should be able to use it to say something more, but we just don't know how. And you might say, okay, so this is not the most impressive structural result you've seen in your life, but keep in mind that we hardly know anything. This is one of the only things we know about sets with few distances, right? That's one of the only results we have.
How sensitive are you to the red O and over root log n?
So, sorry, how sensitive am I for this?
That's right. If I change that to something,
Right. So it's pretty sensitive to this curve. Like if I'm saying just little o of n, for example, yes, I think it's actually kind of hurt the argument a lot. You'll get lines with a lot less points on them. Okay. I suspect that there's no way to have so many lines with log n points without having a line with more points on it. Especially if you also have the constraint that you have fewer distances, but I couldn't do anything with it so far. Okay, so you can come up with other geometric energies, right? What happens if you ask the direction defined by the first 2 points to be the same as the direction by the other two? There are a lot of things you can come up with, and surprisingly, when you start to play with it, things just work. Each time I'm trying to do one of these energies, something interesting happens. And I want to show you a different example. So I said that Misha gave an excellent background for this, because what I wanted to talk about today is the idea of higher moment energies. So in additive combinatorics, one of the tools that are used in recent years is the dth moment energy. Instead of quadruples, you're looking at 2 digits. So Misha was talking about third moment energy. And instead of asking 2 representations of the same sum, you're asking for d representations of the same sum. A1 plus b1 is the same as a2 plus b2, a3 plus b3, etc. And this turned out to be quite useful. A lot of new bounds are constantly being obtained with this. For example, one of the best bounds for Balog-Samredig hours is a work of Sean where he used the third energy. There are best bounds, I think, for sums of convex sets is used by it. Misha saw you other things in his talk before. So very used idea in recent years. And we were thinking, what happened if we tried to look at it for distance energy, for example, or other geometric energies? And surprising, very naturally, we got a lot of new results. So let me give you a couple of examples of new results. So I'll mention another distinct distances problem. There's distinct distances problem that's sometimes called distinct distances with local properties. So we have 3 parameters. It's phi of n, k, l. And this is the minimum number of distances by n points in the plane, just like the original problem, but where the point set is restricted. Now you have a new restriction. You think of k as some constant, maybe 10. So every 10 points, then at least some number of distances. So it's a local restriction. You're saying, if I locally look at a small set of points, they have bad behavior with respect to distances. They have a lot of distances. Can I use this local property to say something global? Can I say something about a total number of distinct distances just by knowing something locally about every set of points? So to see how this works, here's maybe the easiest example. Phi of n 3, 3. Every 3 points need to span 3 distances. So we're not allowing isosceles triangles, that's 3 points with 2 distances, and we're not allowing equilateral triangles, 1 distance for 3 points. What happens now? So fix a point, and we're not allowed to have isosceles triangles, so it has to have a different distance from any other point. Otherwise, we have an isosceles triangle. So it spans n minus 1 distinct distances with the n minus 1 other points. You immediately see that you have at least n distances. Erdős showed that you can have sets that don't have isosceles triangles and have this number of distinct distances. This is, by the way, just Berne's construction. It's very easy. You just use Berne's construction, you get this. So it's another case where we still have a gap, but it's a sub-polynomial gap. It's a very small gap in n, right? Less than polynomial in n. Okay, so this was one easy example. Here's another. Take a k that's at least 4, and let's look at this expression. Minimum number of distances, distinct distances, when every k points must have this weird number of distances. What is that? So ignore this for a second. What is this? This is the maximum number of distinct distances that k points can have. K choose 2, the worst case k choose 2 distinct distances. So basically we're allowing about half a k repetitions. You have k points, you're allowing about half k distance repetitions. And in this case it's also trivial, because it basically says we're not allowing any distance to repeat half a k times. If we have half a k representations of the same distance, we have at most k points with a lot of distance repetitions. Cannot happen. So what we immediately know, every distance repeats a constant number of times, there must be n squared distances. This is another trivial case. Okay, I thought it's interesting to mention, you just change it by 1. If you just change the restriction by a tiny bit from +2 to +1, so you allow one more distance repetition for every k points, it becomes a wide open problem. Instead of just immediately seeing that it's n squared, we know it's at least n to the 4/3. It comes from some paper of Erdős and Sheffer. They studied something slightly different, but it led to this. And suddenly it's somewhere between this and n squared. Tiny change really changes the situation. Okay. Recently, there was a work of Fox, Bach, and Suk, and they show this bound. So what is this bound? Here we allowed for k points to have about half a k repetitions, right? They allowed a lot more. They allowed for every k points to have about k repeating distances, so smaller number of distinct distances is still okay. Ignore this constant, they don't matter much. And you get a weaker bound, but for a weaker restriction. So if you allow more repetitions, you can still say something non-trivial about the number of distinct distances that you can have. Epsilon just means take epsilon to be as small as you like, doesn't matter. Okay, so this is the problem. And we just try to see what happens if we look at higher distance energies for this problem. And we immediately got a new family of bounds. So here's the complicated way of saying this family of bounds. For every d, we get some this restriction with this bound that depends on d somehow, doesn't matter. The point is that, let's see what this means. Let's say that d is 2. When d is 2, we get, so now we allow 2k over 3 repetitions, and we get this number of distances, n to the 1.5 distances. So I like this result because we actually have a lot of distinct distances problems where we expect the number of distances to be very large, close to n squared. And as far as I know, in all of them, we have no techniques for getting more than n to the 4/1 distinct distances. We're always very far from 1.5. And I think, maybe someone will correct me, but I think this is the first time I see a way to get more than n to the 4/1 distinct distances. Still very far from n squared, of course. And if you put d equals 3, the restriction becomes a bit weaker. The bound becomes a bit weaker. We now allow 3k over 4 repetitions and a somewhat weaker distinct number of distances. By the way, the Erdős and Sheffer results show that if you deviate from the trivial bound by 1, you get n to the 4/3. We really extended it a lot. Now this is much further away from the trivial bound and we get n to the 4/3. And this keeps going. You put d equals 4, you get something weaker restriction, weaker bound. You put d equals 5, weaker restriction, weaker bound. At about 7, I think, it gets to be the same bound as Fox, Bach, Suk, and then when you go to 8 and more, our situation becomes worse. Okay, so I'm going to show you how this works. I want to give you an idea to show you how natural this was to use higher distance energies here. But before that, I want to mention another result we got using similar techniques. So, yes.
So d equals 2 is the usual energy or the...
Right, that's what will happen. What will happen? That's a good intuition. What will happen is this will be distance energy, third distance energy, fourth distance energy. Exactly. Yeah, good guess. Okay. So another problem I want to mention is called expanding polynomials. We have here a polynomial in 2 real variables. And we have 2 finite sets of real numbers. And we want to apply the polynomial to everything in its 2 sets. We apply it for every element of A and every element of B. And allocation on A, they show that except for some special cases, you always get something larger, much larger. Basically, you start with sets of n elements in them, except for some special cases, you always get a set of with many more than n elements. This is why it's called expanding polynomial. The function expands the sets. The special cases are kind of, if you look at it, it's kind of, you can separate the x and the y, do different things on them. Okay, the best known bound, the current best bound for this is by Raz, Shari, and Shaimushi. Again, two of them you can also look at the audience. And they showed, this is the important part, they showed any polynomial except the special cases expands to something that's like a to the 2/3, b to the 2/3. You always get at least this expansion. And as far as I understand, I can't say I'm an expert at this type of problems. As far as I understand, this is conjecture still far from being tight. It's expected to do better. And we tried to look at this using similar ideas. So now it's not distance energies, it's some other type of geometric energy. And we got another weird looking result. So we have, for a polynomial and two finite sets, the expansion is at least, so instead of 4/3, we have this more involved expression and a weaker restriction. The restriction now is just that the polynomial is not some linear polynomial in x and y with something applied to this. Okay, what is this bound? What is it good for? So it's good when the sets have structure. If A and B have good additive structure, you get better bounds. In the extreme case, let's say that A and B are sets of n numbers, then the Raz, Shari, Mushi will give n to the 4/3, which is best known bound. If we have a good additive structure, the difference that are very small, you get something that's more than 1.5. So I should say the result works for a lot of types of structure. The first thing we do is differences, so that's what I wrote here. You can obviously replace difference with sum, you can do stuff with product, and you can do stuff with much weirder types of energy. For example, what do I mean weirder types of energy? So what has a good additive structure? We usually mean arithmetic progression or something that looks like an arithmetic progression. It will still work if you have, instead of an arithmetic progression, you take fifth powers of an arithmetic progression or some other weird polynomial of a geometric progression, I don't know. You still get this bound. So in a weird way, let's go back to the bound, it tells you that when a set has some sort of a structure, you can do better. Which is counterintuitive for me because you expect a larger expansion when the set is unordered, right? You expect when there's no order, it will expand more. But that's somehow the harder case. We know how to do it when there is order. Now, all you have to do is solve the case where there's no structure and you improve the problem in general. Okay, and we have other bounds, but I don't want to just bore you with a long list of bounds. So let's just briefly mention another one.
So,
Yes.
So just powers of a progression?
Any polynomial. Any polynomial. If you take, where are we? If you take something nice, like an arithmetic progression, or with gaps in it even, and you apply a polynomial to it, it will still work.
Constant degree.
Yes, of constant degree, right. It's not there are a lot of other types of structure that would not work. For example, you can take square roots of this, and then we don't know what to do. But if you take polynomials, it works. Okay. So let's where am I? Sorry, wrong slide. So we looked at another problem of Velokesh. We're studying the case where you have points on the line and points not on the line. What happens to distances there? And we have some new stuff to say there. And we have all sorts of other problems. I don't want to bore you with too many results. That's not the point. The point is just to try to convince you that once you look at these geometric energies, if you look at it from glasses of someone who's doing additive combinatorics, you start to get all sorts of interesting new things. So let me briefly show you how this works. I chose one of the easiest examples we had, one of the easiest cases. So let's do the case where we have distinct distances with local properties, and we have the 4/3 bound. We're allowed to have this number of repeating distances, we're allowed to have, and we want to show 4 distinct distances. So I'll do a hand waving.
Question, sorry. This K is fixed or forever?
Yeah, the K is fixed. Yes. If it depends on n, then it doesn't work. It's any fixed K.
But the bound does not depend on K. So
No.
like if you fix K very small and you have this property, then you know.
K has to be at least like 6, I think.
And then
6 or 7, and it works for any constant K starting then.
Okay.
Yes. Okay. Okay. I think I might finish a bit early, so do ask me more questions. So we want to show. Okay, so let's take a set of points, m points in the plane that has this nice local property. And we're going to look at the third distance energy. So what's third distance energy? We want to look at 6 tuples of elements from the point set. A1 and B1 has the same Euclidean distance as A2, B2 and A3, B3. That's all we're looking at. Okay. What are we doing with this? Let's define some more things. Let's give a name to the set of distances. Delta is the set of distinct distances, and we care about the size of this set, so let's call the size of this set x. If you forget some notion later, tell me, I'll write it again. And the last thing we need is the number for a distance delta, specific distance delta. What is the number of representation it has? How many pairs of points span distance delta? Okay, just how popular this distance is. And it's very similar to something Misha showed in his talk. Now we can write the third distance energy as the sum of the squares of the cubes of m deltas. Why is that? Because m delta cube for a fixed delta is just how many 6 tuples have 3 times the distance delta. M delta ways of choosing A1 and B1, M delta ways A2 and B2, M delta ways choosing A3 and B3. So we can just write this distance like this. This energy, like this. Okay, and also like standard uses of energy, we can use Holder's inequality, and it immediately tells us the number of 6 tuples is at least n to the 6 over the square of the number of distances. And now we can use the standard idea. You have a lower bound for the energy, let's find an upper bound for the energy. Here's our strategy. We have this lower bound for the energy. We're just going to find this upper bound for the third energy. We immediately get that the number of distances is at least n to the 4/3. Okay? So there's not much new here. It's exactly what you do with energy usually. Okay, how do we get an upper bound for the third energy? So we start by noticing this. Let's say we have a point, and it spans the same distance a lot of times, maybe k minus 1 times. This cannot happen, right? We have k points and a lot of repeating distances, way more than we're allowing. We're allowing, what was it, 3k over 4 repetitions. Here there are about k repetitions. So this cannot happen. You take a point, you cannot have the same distance repeating many times next to this point. Multiply this for every point, and you get that no distance repeats kn times. It's actually smaller, but it doesn't matter. No distance repeats more than kn times in this case. Kind of the unit distances problem is easy in this problem, and with this restriction. Okay, why is this useful? Let's have one more piece of notation. So this is, we already said, m delta, how many times delta appears? How many representation it has as a distance between 2 points? Let's say that k sub j is how many distances repeat a lot of times, at least j times. So k sub j is how many popular distances we have, how many distances appear a lot. We can do a standard dyadic decomposition. Third energy is the sum of the cubes of the representations, as always. Now I just wrote the sum of the same thing, I just grouped them according to how many times each distance appears. At each part of this, I have distances with about the same number of representations, between 2 to the j and 2 to the j plus 1. And why is that good? Because we know a lot about distances with about the same number of representations. The number of representations is at most 2 to the j plus 1, so I can upper bound m delta by 2 to the j plus 1. And the number of such distances is at least, at most, k to the 2 to the j. Right? That's the number of distances that repeat at least this number of times. So I have an upper bound for the third energy. And in a sense, for me the key issue here is that we reduce the distinct distances problem to a problem about popular distances. In a lot of our applications, this is the important part. You use the higher energy to reduce this to a problem about how many popular distances there are, and then you solve it in each problem according to different things that you can use. Okay, so in this case, all we want to do is to show that the number of distances that repeat at least j times is at most n cubed over j cubed. You plug this into the upper bound we have for the third energy, and you'll get the bound that we want. Okay, how do you do that? Also very simple. Let's look at this case. I have a lot of points, all of these blue points, P1, P2, P3, etc. And I have three distances, delta 1, delta 2, delta 3. And the point is that let's assume that P1 spans delta 1 with some point, delta 2 with some point, delta 3 with some point, similarly for P2, for P3, etc. All of these points span these three distances. Then I again have a set of k points with a lot of repeating distances. Delta 1 repeats a lot of times, delta 2 repeats a lot of times, and delta 3 repeats a lot of times. And you can show that there are too many repetitions. We get too few distinct distances, so such a case also cannot happen. You cannot have k over 4 points, each of them participating in these three distances. And that's almost the end of the proof. Why? We actually get a problem about set intersection. What happens here? So we have a set of endpoints. For each distance, popular distance, think about the set of points that span this distance. It's a subset of our set of endpoints. We look at a subset, all the distances that, say, participate in some delta 1. Now, so let's call this P delta. P delta is the set of points that span delta. Now, it's large because we're looking at popular distances, right? All the distances are popular, so it's a large subset. We have a set of endpoints, a lot of large subsets of points, and we just said every three subsets cannot have a large intersection. That was a forbidden configuration. So we got a set intersection problem. If you just have a bound, how many large subsets you can have of n elements with no three intersecting in this number of points, in this number of elements, you'll immediately get an upper bound of the number of popular distances, or the number of subsets. So the way we did it, we found some counting lemma in some old paper of Erdős. I wouldn't be surprised if we missed a better way of doing this that we're just not aware of. And we get, in this case, the number of popular distances is n cubed over j cubed, or the number of subsets of P is at most this. Okay, so this is more or less the end of the proof. Let's think, what did we do? We used the energy, the higher energy, to reduce the problem to a problem about how many popular distances there are. We plug this to get an upper bound for the third energy. We combine it with the easy bound for the third energy with Holder, and we immediately got the bound of the new bound of the number of distinct distances. And as I said, to get other bounds, all you have to do is switch the third energy with, the dth energy, and then you're allowing these subsets to have a large intersection instead of three subsets. So I hope that some of you might agree that this was very natural once you started to look at this. And this happened to us with a lot of problems. Somehow, it was very easy once you start to use this geometric energy to get all sorts of new results for them. So I want to repeat my point. I think there's a lot to do here. It's really an uncharted territory. You can adapt other techniques from additive energies to geometric energies. I mean, so far we did just a few and we got a lot of new results. Who knows what happens when you try more techniques? It would be amazing to have variants of results such as bulk summary Gauss for distance energy. That would be a very big result in discrete geometry. You can just more arbitrarily see what happens when you study other types of geometric energies. There are many energies no one ever studied. I'm not sure what happens if we try direction energy. Maybe you also easily get some nice new results. And I hope that maybe a couple of people in this audience were convinced that it's worth spending time on. And as I said, we're finishing pretty early. Maybe I'll just say I use this for some advertising. Next summer, we're having a graduate school, summer school in polynomial method in MSRI. Send us nice graduate students who are interested in this. That's it. Thank you.
It's 9 like 2 years.
Not this summer, next summer. Yeah, not the summer of this year, the
I
summer.
wish it was summer already.
Yeah.
Okay.
The proof that you showed, is it special to distances, or if you have some like a sum set where every k elements have many sums, or it works the same?
So what problem do you get? What proof? The local properties.
Yeah.
Oh, that's interesting. So you're saying
Did you
every
use, distances?
Oh, that's interesting. Yeah, local properties for additive. Yeah, I don't know. I never looked at it. It's likely to. We use some geometric observations, but maybe you can replace them with additive
So
observations.
what is the part that doesn't work to graph?
So the Erdős gyflash that you said, of course, doesn't use any structure, and will hold for that as well.
Right. It's about coloring of
Just
birds.
coloring.
Right. Right. Yeah. I hope I'm not missing any
So
geometry.
what part are you using that doesn't clear? So in the proof.
Right, so it should work. It's a good point. Right, it should. I can't see anything that doesn't work immediately.
Do you think it will work for graph coloring?
No.
No, so
So we're talking about additive energy. So you have a set of numbers.
okay.
If every 10 numbers don't have too many sums, what will happen? That's interesting. Yeah,
If every 10 numbers have many sums.
yeah, that sounds like a nice thing to look at. Yes.
So you have these two different energies, the additive energy and distance energy. The additive energy is just with that addition, and the distance energy mixes multiplication and addition, something that looks a little bit like sum product phenomena. So you were showing why similar things work for both. Is there something that shows that they're somehow fundamentally very different? And
So the problem is, I don't know. I would suspect so, but we're just starting to study this. So the problem, a lot of classic proofs for additive combinatorics immediately don't work. Like you want to prove value summary Gauss, usually you're using this cancellation that you sum up three things that cancel. You cannot do this here. So I don't know if it doesn't say that you can never do this, but we just don't know enough yet to answer this. But I want to say there are all sorts of conjectures about a nice connection. For example, Netscat's conjecture that the problem about finding structure with sets with few distances, maybe the way to approach it is to show that such sets have good additive structure. You can still look at additive structure of points, right? And maybe that's the way to get more structure for sets with few distances.
So for some difference between sums and distances, which actually goes in your advantage, is that you cannot have the same sum for a plus b and a plus c and a plus d. You could have it in your case, but distances. But here you will not. Here every sum appears as a matching to begin with.
Right, right.
So it's even better.
Right. Oh, yeah, that's a good point. Actually, one immediate difference: additive energy is at most n cubed. Distance energy can get to n cubed log n. So we already have a small difference, and
Yeah.
What do you think?
so it looks like your proof that you show is you could probably modify it and use the normal energy, the normal twofold energy. Have you tried doing that, and what did you get?
yes. So we had a family of bounds, right? We have each time a weaker condition, and then you get a weaker bound. The first one, if you assume, let me use the board for a second. If you assume that the number of distances is k choose 2 minus 2k over 3, you get a bound of n to the 1/2 distances. That was done using standard distance energy. Each time you go to a higher energy, you get a weaker restriction and a weaker bound. So that was one special case of this family of bounds.
That you can't keep the same restriction and
It
use
didn't
different
work.
energy.
Maybe you can do it. I'm happy to talk about this.
It will be because in the lemma you have that every 4 sets intersect in a cross k or something.
Exactly.
5 sets.
Exactly. It's about right.
And then it's this counting.
Yes, it's
Which
just
is basically Zarankiewicz problem, I think. But
yes,
it's
yes,
some.
yes.
So, how well is it understood what the minimum L is for which you get n to the 1 plus epsilon? Could it go below k choose 2 minus k plus 1?
The minimum number here. So unfortunately we don't know, and I kind of avoiding saying this, but Erdős was talking a lot about these problems, and he started with phi of n for 5 and phi of n 5, 9. What is this? So 4 points have 6 pairs. You're basically allowing one repetition. 5 points have 10 pairs. You're allowing one repetition again. We have no idea. These are between n and n squared. This what should be the simplest case in a set. One of the simplest cases we don't know anything about. Yeah, so we're still very far from understanding this problem. We're starting from the easier cases in a sense.
So no distance appears twice.
So 4, 5 means in every 4 points, one distance, there's one repetition at most. If it was 6, it will. Right. And if you allow this, we don't know how to do anything. It's at least n, it's most n squared. Another embarrassing case when we cannot say anything trivial. And this seems like what Erdős was most interested in.
Maybe the question was, do you know that phi n k 100k is not superlinear?
Phi k
Is that an example that's showing?
It's a good question. I don't have an answer immediately. I need to think about this for a few minutes. Maybe someone else from the Jacob or Janusz knows
For
something.
every k you have at most 100k.
At least 100k.
Yes. So we can ask what happens in a very well-behaved example, like points on evenly spaced on the line. No, I'm not sure.
More questions? If not, then let's thank them.
Straightforward way of using it here then is if you use if you just use it in kind of straightforward way, you got the third action. And the magic is somehow that the third doesn't mean that so maybe
Let's say we're going to look at it. Okay, that is like I did not do exact.
Exactly, yes. Yes, I know. like better to think of it as the number of
At some point I'll ask you to show me. I think I'll do the job of
I read the four-term already.
No, other than that, he's,
I read it previously ago, but I will. The whole picture.
you serious?
There was a sub-question that you don't expect to have many orange lines unless there is a line which contains the other side.
It's the factor with the Yakovich.
Yes.
So it's for a constant number of
Yeah, but check the parameters. If you don't need squared, there's still a gap, so you can use up to log n spheres.
right. But in our case, we'll get a really large number of distances also, right?
I don't care about that.
I don't care.
Yeah, that's really fun, but
You don't want to think that there is a distribution with so many lines, logarithms, right?
You could show at least for constants that you're saying it might work for arbitrary. Not for
Not
constants.
Not
arbitrary, but
arbitrary,
log.
but maybe for log. I don't know. You should check that.
Yes.
If you are interested about this, but you might be ready.
I was looking at it for
The number of distances.
It doesn't make sense yet.
I'll
learn some words.
Yeah. But even, I think it's interesting because even if it doesn't work, it still gives you
You know, hearing a lot.
you still do
I don't know why you are wasting your time and then like your algebraic methods. If you do
Unless it has many distinct distances.
You know, it's not open
you will be
for
combinatoric.
yes.
expecting to prove something like that.
But didn't Ben improve this result about the bisector?
No, he improved a different application that I did not mention in this talk at all.
Okay.
So you know how you can use energy to say something about the subset. If you say that the energy is not too large, the subset cannot be too small. It's because small subset means large energy, right?
The small subset.
Small subset immediately.
Subset like a points in the range?
No, this is for numbers. If you have a small subset.
Oh, energy, the standard energy. I'm thinking of bisectors.
It's okay, it's all the same, it doesn't matter. You can
No,
think of
we're
any
doing
energy you
this.
like.
Okay, yes.
So Cauchy first shows you that a small subset means large energy. So by showing that the energy is not too large, you get that the subset cannot be too small. So we had a result that shows you, because we had a bound for the bisector energy, you can show that the bisector set cannot be too small. There must be a lot of bisectors. This was another result. And then improved that in a less naive way. We just did something very simple.
It didn't bound the energy?
No, he did a more complicated argument for
Distinct
how to show.
bisectors.
Okay.
Minimum number of
So
unless there are many on
you wanted to
many on a line or
this
so.
was what they said.
Okay.
If every k have so
A lot of this was I mean, like you said, say everything has at least 100k distances.
Should they stay here, like in the first row?
You should do whatever you want.
No, stay here.
Which kind of system is there?
Serious.
for instance, like in this triangle argument,
Those channels, that's for sure. They like
Okay, if you have a comment,
okay, we did not.
it's a challenge.
Okay.
I don't know. I can't remember if we tried or not exactly about the we definitely would have liked to have thought in that direction. I'm not saying that
we can I'm happy that's 4. We can after the last talk.
We definitely
So the use of
I mean, we had many lines, but now we can square log it's much better half than one line.
No, it's about the
So we definitely want it like
so you can have an algebraic.
Each time I get different amounts for the popular distances. And I kind of trying to use the higher energy.
Yeah, I was just like,
And when I use higher energy, I get a nice lower one.
Yeah.
Yes, exactly. So we had a different application that I didn't do where researchers started using higher energy something like I just like it made me remember it. Let's check and see if we have
I'm impressed by the intuition that you have
Just that's why we had the meeting. Yeah, of course, you organized it from that's why I'm defining. She's very new to learn how to do there are so much to they do
So I thought about this.
Oh, you mean
I think that